Let's consider distributions of charge along an arc. This example shows a semicircular arc that has been charged in a specific fashion. I have put a charge which can be described by the charge density lambda as a function of theta as some constant value lambda naught times cosine of theta. So cosine of theta is equal to 1 when theta is equal to 0. So there are large positive values close to the x-axis indicated by these large plus signs. And then as theta goes to 90 degrees, that charge becomes 0. So I drew that with a small plus sign there. And then beyond 90 degrees, theta starts becoming negative since cosine is negative in the second quadrant. And then it gets to be very big and negative close to 180 degrees. So it's a non-uniform charge distribution given like that. Now I would like to show you two ways to do this problem. One is to just blindly do it by integration using the x and y components, and the other is by using a symmetry argument. Now the symmetry argument can always be used in a situation where the left and the right have a certain symmetry. In this case they do. So let me go over the symmetry argument first. We'll take a small charge element subtended by d theta. So that's going to be our charge element dq. Now we have to know something about the arc geometry of a circle. If the angle is d theta, I haven't told you what the radius is. Let's assume the radius of the circle is r. Then the arc length ds bears the following relationship with d theta. It's equal to r times d theta. As a matter of fact, if you integrate both sides, you're going to get the famous formula circumference equals r times 2 pi, because when you go around once in a circle, the theta will be 2 pi. So that's certainly true. So that's the infinitesimal version of a formula that you already know from your school days. So now that we have the connection between dq and lambda, we can immediately write everything in terms of the density function. Remember what we have earlier, lambda is also equal to the rate of change of charge with distance. In this case the distance is the arc length. So I'll get dq equals lambda times ds, which is r d theta. In this case lambda is equal to lambda naught cosine theta, so you put that there and then you're all set. Now the vector nature of the electric field must be taken into consideration. Our aim is to find the electric field at the origin due to this arc shape. So one way to proceed is using symmetry, as I said. This particular charge element is going to put an electric field out like that. Remember, it's a positive charge element, so it'll push the electric field out at the point P, which is the origin. If you take the mirror symmetric element located at the same angle theta from this side, then that'll be an electric field that would be sucked in, since it's a negative field. So you can clearly see that the y components are going to cancel and the net electric field is just going to be along the x direction. So that's going to be the electric field at point P. It's going to be in the negative x direction. So one option is to use a symmetry argument and simply calculate just that component. So I would say that by the symmetry argument, by symmetry, E sub p, dE sub p rather, is simply equal to dE. That angle is also going to be theta, by the way. 2 times dE cosine theta. And then I'll proceed to evaluate this, because dE is k dq over r squared times cosine theta. And then you integrate both sides to find what the electric field is, and the direction you can simply say it's to the left. So that's one option. The other option is to not worry about symmetry and simply calculate it using vectors. And that's an approach I want to also show for those who are not very keen on the symmetry argument. The only problem with this second approach is that you have to take into account that DE has got both x and y components. So if you're not worrying about the mirror element and you're only talking about the element there, then this DE vector has to be decomposed into the x component and the y component. So let me write the DE vector in full. It's going to be DEx I hat plus DEy j hat. Now the x component of the DE vector is negative DE cosine theta because it's acting to the left. And the y component is also going to be negative because it's acting down. Okay, now we can put what DE is. DE is k dq over r squared. Let me take that common outside. And then I have here cosine theta I hat plus sine theta j hat. dq is lambda times rd theta. So let's put that there. And lambda itself is lambda naught cosine theta. So I'll write everything at once. Lambda naught r cosine theta d theta divided by r squared times cosine theta I hat plus sine theta j hat. One of the factors of r cancels out. Now there's really nothing I can do at this point except to integrate, so let me do that. E is going to be the integral of dE. Now if I'm not using the symmetry argument, I don't have to worry about the mirror element being used, so I can simply go from 0 to pi all the way. I'll bring out the negative k lambda naught over r outside since they're all constants. So I get integral 0 to pi. Let me go and multiply this cosine theta in. So I'm going to get cosine squared theta I hat plus cosine theta sine theta j hat d theta. Don't be flustered by having a vector quantity inside the integral sign. It just means that you do them separately. So you can think of it as two separate integrals. In fact, let me do that. This is k lambda naught over r times the integral from 0 to pi cosine squared theta d theta I hat minus k lambda naught divided by r integral 0 to pi cosine theta sine theta d theta j hat. Now remember, at the end of the day, we are supposed to get only the I component. The j component is going to vanish because according to our symmetry argument, only the I component survives. So let's try to figure out why the j component vanishes. Cosine theta times sine theta can be written as sine 2 theta divided by 2, because sine 2 theta is 2 sine theta cosine theta by the familiar trigonometric identity. Now cosine squared theta, how do you integrate cosine squared theta? For that you have to use the half angle identity. If you've forgotten them, now I myself don't remember these things, at least remember one identity, and that is cosine squared theta plus sine squared theta equals 1, along with this identity of cosine 2 theta. Cosine 2 theta is cosine squared theta minus sine squared theta. Now if you have this, you can see how you can get cosine squared theta alone. Let me write sine squared theta as 1 minus cosine squared theta. So I'll get this as cosine squared theta minus 1 plus cosine squared theta, or 2 cosine squared theta minus 1, from which I can solve for cosine squared theta. So I get cosine squared theta is 1 plus cosine 2 theta divided by 2. Well, that's what I'm going to use here. So I'm going to get negative k lambda naught over r. I'll take the 2 outside, and the integral of 1 plus cosine 2 theta. Well, the integral of 1 is just theta, and the integral of cosine 2 theta is half sine 2 theta. Because when I differentiate sine 2 theta, I get 2 times, which cancels this half, cosine 2 theta. From 0 to pi. And what about this integral here? That half comes outside, so I get k lambda naught over r, and the integral of sine 2 theta is negative cosine theta. Cosine 2 theta, because of the 2 there, you have to further divide by 2. And there's also the 2 from earlier. So that goes from 0 to pi. All right, this is, I forgot 2 things, the I hat here and the j hat there. Let's evaluate this. Now the sine 2 theta at pi limit and at 0 limit contributes nothing, so that goes away. And I just have this theta term here. So that's negative k lambda naught over 2r times pi I hat. Now this term, let's look at that term. It's k lambda naught over 4r. The integral, the limit, which is cosine of 2 pi minus cosine of 0. Cosine of 2 pi and cosine of 0 are the same. They're equal to 1 each. So this is 1 minus 1, or 0. And we correctly recover the result that you only have a I component and no j component. Which is consistent with our expectations from the symmetry argument. So in this manner, we have solved an example of finding the electric field due to a charge distribution using either the symmetry argument or using methods of vector calculus.